Welcome to Building Resilience, a podcast by Hatch for insights around risk management for sound business practices. I'm Joelle Pang,
And I'm Mert Zain.
your host for today's episode.
So today we have Dr. Pouya Zangeneh with us. Pouya is a risk analytics specialist, heading the risk analytics service line within Hatch's risk management group. He is a professional engineer and recently finished his PhD focusing on knowledge representation and probabilistic methods to quantify, measure, and model social and technical risks and corresponding losses. Pouya has a wide range of experience working in projects within the mining and metals, infrastructure, and energy sectors. Welcome, Pouya.
Thank you very much. Thank you, Mert. Thank you, Joel. Thank you for having me. And yeah, I look forward to our conversation today.
Excellent. So let's dive into it. We've recently read your blog post and wanted to speak with you further. But before we deep dive into the topic, let's revisit the blog posts. You discussed the normal distribution of risk events in your blog post and covered the unwanted consequences as tail ends of the distribution. Now, can you elaborate on this? What are the fundamental differences in quantification of risk events? How do we apply statistics modeling to deal with low likelihood, high impact, so-called black swan events?
Definitely. Thank you very much, Mert. Yeah, that was a quick blog post that I wrote and I enjoyed writing it. I should just mention that the goal of the blog post was that not everything is distributed normally. So I was saying that in the blog post that things are often not distributed normally. And I was trying to address this idea of heavy-tailed or like infrequent high consequence events, right? The idea is that it is useful to think of risk as a tail of a probability distribution, that you always have like your expected outcomes in the middle. Say, now it's good to think of a normal distribution. Say in the middle of that bell curve, you have your expected outcomes. And then the risk is often those unwanted outcomes that would be at the tails, right? So therefore, you can think like modeling risk is essentially modeling those tails. And now we can quantify the tails for normal distributions quite well. And most of our statistical tools, such as this famous theorem called central limit theorem, are essentially based on similar distributions like normal distributions, right? But some events are not normal. They have heavier tails. They have tails that do not decay the same way as the normal distribution does. And therefore, our approximations for those tails, when we use normal distribution theorem or methods that are built on it, are essentially wrong. So we may think that a certain risk is, for instance, 1 in a 10,000 years event, but in fact, it happens as 1 in 1,000 years event, and so on. And there are different keywords to refer to this phenomena. Some call them heavy-tailed events, some call them power law distributions. Black swan events are essentially being used to refer to the same thing, but all referring to the same idea that normal decay is violated, and we need to use rather more sophisticated statistical means to deal with them.
So now that we understand a bit more about what normal distribution and the central limit theorem are, what are qualities of events and the nature of processes that tend to fall outside of the central limit theorem? And can you give us an example of that?
Yes, definitely. That is a great question, Joel. So it comes back to the data generating process. It's not a very common thing. Most of the distributions that we deal with are essentially having a stable decay, let's call it that way. But some of them then are not. And sometimes when there are multiplicative processes within these different processes, that multiplicative nature of them can violate that stable decay of the tails. But when we think about it, many of the disasters and important, catastrophic events that we deal with them frequently in terms of dealing with nature or otherwise are just like that. Like earthquakes is a textbook example. There is a tectonic energy buildup, that multiplicative process that manifests as an earthquake. But the same thing is true for, let's say, cost overruns of projects. That is the same thing, different items lead to each other multiplicatively. and build up that rather black swan event or heavy tail. And you can go on and on, like dam failures. Most of these catastrophic failures are essentially a result of that multiplicative process. And, central limit theorem, for instance, states that the sum of such random variables would be normally distributed. But it doesn't matter if you have, if you have 100 different variables, if 99 of them are normally distributed, or they have, that stable decay, but only one of them is not, that would violate everything. That would violate the way these statistical theorems work. So we got to be very cautious of the data generating process and essentially try to model that step by step to deal with this. And which is something that we at the Risk Analytics and Resilience service line here in Hatch, we are trying to do.
How about dealing with those type of situations where historical data is not available? And we kind of covered this in other podcast episodes that we've conducted, where we've talked about events that has never happened, perhaps at a site, or that has never happened in the history of the world. So therefore, you cannot predict its likelihood. What are some of the biases we may have in this process?
That is a great question again, Merit. So you said it right. Sometimes we have data, and once we have data, essentially what we need to do is much simpler, right? Although still we have to be careful of that data generating process and check signs within our data, whether we are capturing that process and what would be essentially the distribution that we are trying to deal with. But as I guess all of us are quite frequently seeing with the problems that our clients have within the industry, many of the times we do not have enough data. Or there is something or some problem that we just realize it is important and we are just starting to collect data. So it is in fact a bit counterintuitive what I'm going to say, but when we are dealing with modeling risk, often those first few data points are the most important ones. So in those cases, like we need to sit with experts trying to look into the old data or trying to find a certain understanding of the process. But then the first few data points that we can get hold of are the most important ones, as they reduce the risk quite drastically. And we use different types of probabilistic methods to deal with them. Bayes theorem is essentially something that we use. And yeah, so we can start from the expert judgment or the old data that we have, and then we can try to update it step by step in search of that true probability. And in fact, we can do a little experiment today right now. There is this interesting example of these Bayesian probability updating that I first read it in a book written by Douglas Hubbard. But I thought it's very interesting and it could use like expanded FAIR there to really show the process. Are you guys in to do a quick experiment?
Definitely.
Okay, this is becoming famous really in my discussions with clients and such. So Mert, let us assume that you are our expert on jelly beans, right?
Okay.
And Joel, I'll get back to you. So let us assume that you're an expert on jelly bean, and I'll ask you, Mert, give me your expert opinion on a weigh of a single jelly bean, and give me like a 90% confidence interval.
Okay, great question. Let me think
For
about
a single jelly bean.
For a single jelly bean, I'd say between 1 gram to 5 grams.
Perfect. That's good. So that is often what we get from the experts, right, on specific questions that we may have, right? And then now I get that. I'll talk with Joel, who is our risk expert. And Joel tells us that, you know what, we know, for instance, that for the jelly beans heavier than 4 grams or 3 grams, let's say, there is a risk of choking hazard, right? Now, starting from 1 gram to 5 gram, there is a huge risk of choking hazard. Essentially, I think more than 30% on there. Like if you assume a bell curve that goes from 1 to 5, more than 30% there is a risk of choking hazard. But then I tell Joel, who is our expert, that I say, you know what, I found this one data point, this first data point. I find a jelly bean and I did weigh it and it was 1 gram exactly, or 1.1 gram. So I ask you, Joel, now what do you think about that interval? How do you update that if you just want to go common sense about it? Like how would you update that 1 to 5 gram interval?
I would update the interval by reducing the upper limit, so maybe down to 3 or 4 versus keeping it at 5.
Perfect. That's how our brain works. And the way our brain deals with it is in fact quite Bayesian, I should say. So now having this one data point, Joel reduced that 1 to 5 to, let's say, 1 to 3, right? Now I'll give you, Joel, another data point. Let's say another jelly bean, I weigh it and it was 1.1 gram again. Would you update that still?
Yes, I would update it again, maybe down from 3 to 2.
Perfect. So what we have to notice here is that that choking risk hazard, which was for jelly beans above, let's say 3 grams, it just completely off, right? So we kind of moved from that expert judgment with our updated understanding of the probabilities based on just 2 data points. And this is a procedure that there is a mathematic equivalent of it called Bayesian probability updating, right? And when it comes to risk, which is that tailed proposition, the tail of the distribution, it is really helpful and powerful, and we are trying to replicate the same thinking when we are dealing with industrial problems for which we do not have enough data. And as we collect more data, we arrive at that true probability of a jelly bean, whatever it is. But the first few data points are really the ones that are helping us a lot with the risk. Thank you very much. That was a very good experiment that we.
Thank you.
Thanks, Pouya. Yes, that definitely was a great example. Now, I would love to connect this approach to a problem that is near and dear to me, climate change. So we know that as climate change accelerates, natural catastrophes are becoming more common, and it's important to manage these physical risks. Can you tell us how these risks are calculated in the industry?
Well, of course, Joel, and I do share the concern with you, and I'm really glad to see the industry as a whole is going towards that and considering the effects of climate change. It's a very, very complicated problem to deal with. I would start by saying that natural catastrophe modeling scientists and in fact, the insurance industry really they have perfected this realm of science that they call natural catastrophe modeling. And where essentially what they do is that through a series of Monte Carlo simulation, really sophisticated ones, let's say, first of all, they simulate like 10,000 years worth of events of, let's say, hurricane or cyclones. And then they try to do these processes of data generation through Monte Carlo, as I mentioned, to arrive at potential losses of certain natural catastrophe events, right? However, the climate change is really a new phenomenon. So we do not know how the climate change affects that simulated catalog of events, if you will. There are ways to deal with that. One very powerful way of dealing with that is this notion of Bayesian probability updating, right? So that is definitely one of the great areas where these methods can be applied. The other thing that I would add to that in terms of dealing with these extreme events, extreme weather events, is the interdependencies on the ground, right? So once we deal with like big industrial processes, they are not just single store that we can calculate that through those Monte Carlo simulations, the loss for it, especially for business interruption. They are very much connected. They are part of a connected network where one part of it, if it goes down, it would bring the whole network down. So that is also another area where we, using these really Bayesian probabilistic methods, we can try to model quite well. And we've been part of interesting projects dealing with, helping our clients, I should say, in dealing with such problems, actually.
Fantastic. Okay, well, thank you, Pouya. It's been absolutely a pleasure to have you on the show. I'm sure our listeners also appreciate the scientific approach to risk analytics.
Perfect. Thank you very much. Thank you, Mert and Joel, for having me. I think this podcast is a great initiative that you guys are leading, and it really shows the diverse set of expertise that we have here in Hatch. I want to also invite your audience to reach out to us. We at the Risk Analytics Group are helping our clients in dealing with many of their complex risk problems, and we'll be certainly happy and glad to sit with you and share our expertise. Thank you very much.
Thank you, Pouya. Thank you, Mert. Thank you all for tuning in. And if you enjoyed this episode, don't forget to like, comment, and share. For more information on risk management business solutions, visit hatch.com to learn more about creating positive change together.